Today's topic is Bellman Ford algorithm. Like Dijk's algorithm, it is used to solve single source shortest path problem. However, it is slightly better than Dijk's algorithm since it can successfully calculate negative weighted age graph. As you can see, this graph is a negative weighted age graph since this age has a negative weight. If we try to calculate the distance from A to B, it would be 4 minus 2 is equal to 2. A to C would be 3 minus 2 is equal to 1. But but let's try to solve this using Dijk's algorithm. In the previous video, we saw that to solve Dijk's algorithm, we'll have one distance array where we'll sort the shortest distance from A to all other vertices, and a table which will contain the list of visited vertices. So at first, let's put down a source with its distance. So a comma 0, it's going to be our new source. So a comma 0. The adjacent vertices are b and c. So b comma 3 and c comma 4. Between these two, clearly b is smaller. The distance of b is smaller. So b comma 3 is our new source. And if we calculate the distance of C via the B path, so it would be dist of B plus cost of B comma C. So 3 minus 2 is equal to 1. So the new distance of C is 1 since it's smaller than 4. So C comma 1. We forgot to update the distance of B in the dist array, so from infinity it would be 3. C comma 1 is our new distance, sorry, new source. So the distance of C will be updated as well from infinity to 1. So using Dijk's algorithm, we can see that the the shortest distance of B is 3 and the shortest distance of C is 1. But it is not correct, right? Because we previously calculated the shortest distance from A to B is 2. So Dijk's algorithm cannot successfully calculate the shortest distance from the source to all other vertices if the graph has a negative age. But Bellman Ford algorithm can do that, so we will be learning Bellman Ford algorithm today. Bellman Ford algorithm relies on the concept of age relaxation. Relaxing an age means updating the shortest distance via an age. Meaning, if the distance of vertex V is greater than the distance of vertex U and the cost between these two vertices, then we will update the distance of V to distance of U plus cost of U comma V. This is known as age relaxation. Let's say there are n number of vertices in a graph. In that case, in a path, the maximum number of edges can be n minus 1 times. We can understand the concept by looking at this example. Here we have 4 vertices, 1 to 4, and the maximum number of edge can be in a path if we connect all the vertices from the source to that vertex. So we can see here the maximum number of edge is 1, 2, 3. The total number of vertices was 4 and the total number of edge we found was 3. So we can say the maximum number of edge, if there are n number of vertices, it would be n minus 1. So if we relax all the edges n minus 1 times, then we will surely find out the proper distance from the source to all other vertices. And this is the concept of Bellman Ford algorithm. If a graph contains a cycle which has negative weight in total, we'll not be able to find out the shortest path even with using Bellman Ford algorithm. For example, in this graph, this cycle has the total weight of -1, which means the total weight is negative. So let's try to find out the shortest distance from source A to all other vertices. At first, the distance of A to A is 0, A to C is infinity, and A to B is infinity. Now let's try to relax all the edges. From A to C, the edge weight is 4, so we'll update the distance from infinity to 4. 4 minus 8 is -4, so let's update the distance of B to -4. 4 plus 3 is -1, so it is smaller than 0. That means the distance of A to itself would be -1. So -1 plus 4 is 3, so which is smaller than 4. So the new distance would be 3. 3 minus 8 is -5, smaller than -4. So we'll again update the distance to -5. -5 plus 3 is -2, which is smaller than -1. So we'll change the distance from -1 to -2. And this would go on for infinity, and we wouldn't be able to find the actual shortest path from the source to any other vertices, even with using Bellman Ford algorithm. So if a graph has negative weighted cycle, in that case, we'll not be able to find out the shortest distance from the source to any other vertices. We are given a graph. Now we have to find out the shortest path distance from A to all other vertices. The step one is to list all the edges of the graph. So we have listed down all the edges of this graph. The second step is to relax all the edges n minus 1 times. So this table will contain all the values of the edge relaxations. So at first, the distance of A to A is 0, and from the source to all other vertices is infinity. So we have written down as such. Now let's start the first iteration. From A to B, the distance is 6. So 0 plus 6 equals to 6, which is smaller than infinity. So it's going to be 6. The distance of A to C is 4. So 0 plus 4 equals to 4. The distance of C would be 4. A to D is 5. So the distance is 5. B to E is -1. So 6 minus 1 equals to 5. Let's subtract the distance of E from infinity to 5. And the distance of C to E is 3. 4 plus 3 is equal to 7, which is greater than 5. So we will not be changing the value. C to B is -2. So 4 minus 2 is equal to 2. So we will change the distance of B from 6 to 2. D to C is -2. So 5 minus 2 equals to 3. So we'll also change the distance of C from 4 to 3. G to F is -1. So 5 minus 1 equals to 4. So the new distance of F is going to be 4. E to F is 3. So 5 plus 3 is 8, which is actually greater than 4. So we will not be changing the distance of F. Our first iteration is done, so now let's start the second iteration. A to B is 6, 6 is greater than 2, so we'll not be changing that. At first, let's write down the previous values, 2, 3, 5, 5, 4. A to C is 4, which is greater than 3, so we'll not be changing the value of C either. A to D is 5, it's already written down as 5, so no changes. B to E is -1, so 2 minus 1 equals to 1, and which is actually smaller than 5, so we will be changing the value of E from 5 to 1. C to E is 3, 3 plus 3 is 6, which is greater than 1, so no changes. C to B is -2, 3 minus 2 equals to 1. So we'll change the value of distance b from 2 to 1. And d to c is minus 2. So 5 minus 2 is 3. It is written down as such. D to f is minus 1. So it will remain 4. E to f is 3. 1 plus 3 equals to 4. So there is no changes in that case either. Let's start the iteration 3. A to B 6, no changes. A to C 4, no changes. A to D is 5, again no changes. B to F is minus 1. 1 minus 1 is 0, so we will change the value of E from 1 to 0. C2 is 3, so no changes. C to B is minus 2, so 3 minus 2 is 1. It is written down as such. D to C is minus 2, 5 minus 2 is 3. Again, the distance of C is 3. D to F is minus 4, no changes, but in this case, E to F is 3. 0 plus 3 equals to 3, so we'll change the distance of F from 4 to 3. Let's start the fourth iteration. In the first three ages, there would be no changes because it's greater than the distance already. Uh, B to E is minus 1, 1 minus 1 equals to 0. It is written down as such. C to E is 3, which is greater than 0. C to B is minus 2, which is 1. D to C is minus 2. 5 minus 2 equals to 3, so no changes. D to 5 is minus 1. 5 minus 1 equals to 4, which is greater than C, so we'll not be changing the distance of F either. E to F is 3. 0 plus 3 is 3. It is written down as such. As we can see from the previous iteration 3 and iteration 4 has the same value, which means we have found out all the shortest distance from the source to all other vertices, since there are no changes to the distance in both of these iterations. So this is our final answer. And this is exactly how the Bellman Ford algorithm works.